The night sky over the steppes of Central Asia shimmered with a brilliance unknown to those who would come millennia later, when the lights of cities would drown the ancient pathways of stars in a pale orange glow that rose like fog from the earth itself. In the year that later chroniclers would mark as 3200 before the Common Era, a Sumerian priest-astronomer named Enlil-Nairdin stood atop the ziggurat of Ur, his bare feet cold against the mud-brick steps still radiating the day's heat into the cooling desert air. He had climbed these sacred stairs every third night for 17 years, carrying clay tablets and a bronze stylus, recording the movements of what his people called the Heavenly River, that luminous band stretching from horizon to horizon, like spilled milk across the obsidian dome of night. The metaphor was not his own, but inherited from generations of watchers who had stood in this same spot, their names now lost to the relentless erosion of time and windblown sand, yet their observations preserved in cuneiform pressed into clay that would outlast the very civilization that produced it. Enlil-Nairdin did not know, could not know, that he was gazing upon the cross-section of a vast disk of stars, a cosmic wheel rotating in the void with such ponderous majesty that its movement would remain imperceptible across 10,000 human lifetimes. What he did perceive, with the clarity that comes from patient observation unmarred by preconception, was that certain stars within this river moved against the background of their companions, wandering like shepherds among the fixed flock of distant lights. The Greeks, inheritors of Mesopotamian astronomical knowledge through the intermediary of Egyptian scribes and Phoenician merchants, whose ships carried not only tin and amber but also tablets of numbers and diagrams sketched on papyrus, would later call this band the Galaxias Kaiklos, the Milky Circle, from which our word galaxy descends through Latin and into the vernacular tongues of Europe. But the naming itself reveals a fundamental misunderstanding that would persist for more than 2 millennia. The Greeks conceived of the Milky Way as a phenomenon of the upper atmosphere, perhaps a reflection of sunlight off some crystalline sphere, or as their most enduring myth claimed, the spilled breast milk of the goddess Hera as she suckled the infant Heracles, that drop of divine nourishment scattered across the heavens. Democritus of Abdera, that strange atomist philosopher who lived in the 5th century before the Common Era and whose works survive only in fragments quoted by later writers who often disagreed with his materialist cosmology, proposed something far closer to the truth, that the Milky Way consisted of countless stars packed so densely together that their individual lights blurred into a continuous glow. His contemporaries dismissed this notion as the fantasy of a man who saw atoms everywhere, who reduced the gods themselves to chance collisions of invisible particles falling through an infinite void. Aristotle, whose authority would dominate Western thought until the Renaissance, rejected Democritus's stellar hypothesis in favour of an atmospheric explanation, and for nearly 2,000 years, the weight of the philosopher's pronouncement settled over the question like a stone sealing a tomb. In the year 964 of the Common Era, in the city of Shiraz, within the boundaries of what chroniclers knew as the Buyid dynasty's Persian territories, the astronomer Abd al-Rahman al-Sufi completed his Book of Fixed Stars, a comprehensive catalogue that corrected and expanded upon Ptolemy's ancient Almagest, through centuries of Islamic astronomical observation. Al-Sufi, working in an age when the House of Wisdom in Baghdad had already been translating Greek and Sanskrit texts for over a century, when Arabic numerals and the concept of zero had revolutionized mathematical calculation, and when the astrolabe had become an instrument of such precision that navigators could determine latitude to within a fraction of a degree, observed what he called a little cloud in the constellation later named Andromeda. He could not have known that this faint smudge of light, barely visible to the naked eye on the clearest nights, was itself a galaxy, a sister to the Milky Way, containing hundreds of billions of stars and lying at such an incomprehensible distance that the light he perceived had begun its journey toward his eye when his ancestors were still riding with the armies of the Sassanid Empire. Al-Sufi's observation meticulously recorded in Arabic script on vellum pages, illuminated with diagrams of constellations rendered in the angular geometry that Islamic art permitted, would remain the earliest documented sighting of what later European astronomers would catalogue as M31, the Andromeda Galaxy, though they would not recognise its true nature for another 1,000 years. The Italian peninsula in the winter of 1609 was a patchwork of competing powers. The Spanish Habsburgs controlled Milan and Naples. The Papal States stretched across the centre like a belt cinching the boot. Venice remained a mercantile republic whose influence had waned since the Ottoman conquest of Constantinople and the opening of Atlantic trade routes. And in Florence, the Medici Grand Dukes patronised artists and natural philosophers with the wealth accumulated through banking and the wool trade. In Padua, where the university had been teaching medicine and natural philosophy since 1222, Galileo Galilei, a mathematics professor with chronic money troubles and a talent for improving upon the inventions of others, heard rumours of a Dutch spectacle maker who had placed 2 lenses in a tube to make distant objects appear near. Within months, working in the cluttered upper room of his house on the Via Vignali, surrounded by half-finished experiments, military compasses of his own design that he sold to supplement his university salary, and books whose margins were dense with calculations, Galileo had constructed a telescope that magnified objects 20 times, a device that transformed the heavens from a realm of philosophical speculation into a territory that could be explored, mapped, and measured. When he turned this instrument toward the Milky Way on a clear January night in 1610, he saw what no human eye had ever witnessed. The luminous band resolved into innumerable stars, so densely packed that the telescope's limited field of view could not encompass them all. A discovery that vindicated Democritus across the gulf of 2,000 years and demolished the Aristotelian conception of the cosmos in a single observation. The publication of Siderius Nuncius, the starry messenger, in March 1610 consisted of only 24 pages printed in Venice, but those pages contained observations that would fracture the crystalline spheres of medieval cosmology beyond any possibility of repair. Galileo described the moons of Jupiter, worlds orbiting another planet just as Copernicus had dared to suggest the planets orbited the Sun, the phases of Venus that confirmed heliocentric motion, the mountains and valleys on the moon that proved celestial bodies were not perfect spheres of quintessence, but rough terrestrial globes like Earth itself, and the resolution of the Milky Way into stars, countless suns scattered through space at varying distances. Yet even Galileo, with his revolutionary telescope and his willingness to challenge ancient authority that would eventually bring him before the Roman Inquisition, could not conceive the true scale of what he observed. He imagined the Milky Way as a region of particularly dense stellar population within a cosmos that, while larger than the medieval conception, remained bounded, with the stars perhaps a few thousand times more distant than the Sun. The actual dimensions of the galaxy, and the reality that the Sun itself was merely one star among billions within a vast rotating disk, lay beyond the conceptual framework available to 17th century natural philosophy, hidden behind a barrier not of technology but of imagination. In the coal-smoke-choked London of the 1780s, where the Industrial Revolution was beginning its transformation of human society from agrarian patterns that had persisted since Neolithic times into something unprecedented in the history of civilization, William Herschel, a German-born musician who had fled Hanover to escape conscription during the 7 Years' War, and now earned his living as an organist and composer in the city of Bath, devoted his nights to grinding telescope mirrors in the basement of his house on New King Street. His sister Caroline, who had followed him from Hanover and whose own considerable talents as a singer he had co-opted into his astronomical obsession, stood for hours in the cold workshop, reading numbers by candlelight as William called out measurements, her hands cramped from recording observations in the systematic catalogues that would eventually list thousands of nebulae, double stars, and celestial objects whose nature remained mysterious. The Herschel's telescopes, products of William's obsessive perfectionism in grinding and polishing specular metal to achieve reflecting surfaces of unprecedented precision, were the finest instruments of their age, capable of gathering more light and revealing fainter objects than any previous devices, and William employed them not in casual stargazing, but in a systematic survey of the entire visible sky, spending years in what he called sweeps, methodically scanning across the heavens and recording everything the telescopes revealed. On the night of March 13th, 1781, during one of these sweeps, Herschel observed an object in the constellation Gemini that appeared as a small disk rather than a point of light, and over subsequent nights of observation it moved against the background stars. He initially believed he had discovered a comet, a not uncommon occurrence for diligent observers, but calculations of its orbit by mathematicians across Europe soon revealed that this object moved in a nearly circular path far beyond the orbit of Saturn, which since ancient times had been considered the outermost planet. Herschel had discovered Uranus, the first planet found in the age of the telescope, an achievement that brought him instant fame, election to the Royal Society, a pension from King George III, who became his patron, and the freedom to abandon music entirely and devote himself to astronomy. Yet his discovery of Uranus, though it doubled the known size of the solar system and earned him immortality in the annals of science, was merely a prelude to his investigations into the structure of what he called the sidereal heavens, the vast arrangement of stars among which the sun itself was situated. Herschel approached the question of the Milky Way structure with a method that mixed brilliant insight with inevitable error. He assumed that all stars possessed roughly equal intrinsic brightness, which meant that apparent brightness indicated distance, with fainter stars being more remote than brighter ones, and he further assumed that his telescopes could penetrate to the very edges of the stellar system, so that when he looked in a particular direction and counted stars, the number he tallied reflected the true extent of the heavens in that direction. Using this methodology, he conducted what he termed gauges, counts of stars visible in the telescope's field of view across different regions of the sky, and from these numbers he constructed a model of the galaxy as a flattened disk, irregular in outline, with the sun located not far from its centre. The model was wrong in many particulars. Stars vary enormously in intrinsic brightness. His telescopes could not penetrate to the galaxy's edge, and the sun lies far from the galactic centre. But the fundamental conception of the Milky Way as a disc-shaped system of stars was correct, a triumph of observational astronomy and geometrical reasoning that, despite its flaws, represented the first serious attempt to map the three-dimensional structure of the galaxy. Caroline Herschel, often relegated to a footnote in her brother's achievements by generations of historians who could not imagine a woman as an independent scientific contributor, discovered 8 comets on her own, compiled catalogues that corrected errors in existing astronomical references, and after William's death in 1822, produced a comprehensive catalogue of nebulae that served as the foundation for subsequent generations of deep sky observation. She lived to the age of 97, surviving long enough to receive the Gold Medal of the Royal Astronomical Society in 1828, decades before the Society would permit women to become full members, and to witness the beginning of a new era in astronomy, driven by a technology that William's purely reflecting telescopes could not employ: the spectroscope, which split starlight into its constituent colours and revealed the chemical composition, temperature, and motion of distant suns. The spectrum of starlight, that rainbow band crossed by dark lines where specific wavelengths had been absorbed by elements in a star's atmosphere, became the Rosetta Stone of astrophysics in the late 19th century, transforming astronomy from a science of positions and motions into one that could analyse the very substance of celestial objects. In 1842, Christian Doppler, an Austrian mathematician teaching at the Technical Institute in Prague, published a paper proposing that the observed frequency of a wave would shift depending on the relative motion of source and observer, a principle that applied equally to sound and to light. By the 1860s, astronomers were measuring the Doppler shift in stellar spectra, determining whether stars were approaching or receding from Earth by the displacement of their spectral lines toward the blue or red ends of the spectrum, and these measurements revealed something entirely unexpected. Stars were not fixed in the firmament but moved through space with substantial velocities, sometimes exceeding hundreds of kilometers per second. The Milky Way was not a static arrangement, but a dynamic system in which hundreds of billions of suns pursued individual orbits around some common center, a cosmic mechanism of such scale and complexity that the human mind struggled to encompass it. In the mountain observatory at Lick, perched atop Mount Hamilton, in the dry hills east of San Jose in California, where the seeing conditions allowed astronomers to take advantage of the 36-inch refracting telescope, then the largest in the world when it began operation in 1888, James Keeler turned the great instrument toward the nebulae that William Herschel had catalogued a century earlier. Using a spectroscope attached to the telescope, Keeler examined the light from these fuzzy patches and discovered that many showed spectral lines characteristic not of glowing gas, but of starlight, and furthermore, these lines were Doppler shifted by enormous amounts, indicating velocities of recession that reached hundreds or even thousands of kilometers per second. The implications of these observations remained murky because the nature of the nebulae themselves remained in dispute. Were they clouds of glowing gas within the Milky Way, regions where new stars were forming from the condensation of primordial matter, or were they, as the philosopher Immanuel Kant had speculated in 1755, island universes, separate galaxies comparable to the Milky Way itself, but lying at such vast distances that they appeared as mere smudges of light even in the most powerful telescopes? The debate between the island universe hypothesis and the conception of nebulae as intragalactic objects became one of the central controversies of early 20th century astronomy, a dispute that hinged not on philosophical preference, but on measurable quantities. The distances to the nebula, which remained maddeningly difficult to determine. In April 1920, the National Academy of Sciences in Washington hosted what became known as the Great Debate, a formal discussion between Harlow Shapley of the Mount Wilson Observatory and Heber Curtis of the Lick Observatory concerning the scale of the galaxy and the nature of the spiral nebula. Shapley, who had recently completed groundbreaking work on the distribution of globular clusters, those dense spherical collections of ancient stars that orbited the galaxy like satellites, argued that the Milky Way was far larger than previously believed, perhaps 300,000 light-years in diameter, with the Sun located not near the centre, but in the outer regions of the disk. If the galaxy were truly so enormous, Shapley contended, then it could easily contain the spiral nebulae as subsidiary structures, and there was no need to postulate the existence of external galaxies. Curtis countered with evidence that the spiral nebulae were symmetrical, independent systems, that their spectra resembled those of unresolved stars rather than glowing gas, and that novae observed in these nebulae appeared far fainter than novae in the Milky Way, suggesting tremendous distances. Neither man could prove his case definitively because the technology of the time could not measure the distances to the nebulae with sufficient accuracy. Though ironically, both were partly correct. Shapley's revised model of the Milky Way size and the Sun's eccentric position was essentially accurate, while Curtis was right about the extragalactic nature of the spiral nebulae. The resolution of the debate came 4 years later, not through further argumentation but through observation, when Edwin Hubble, using the 100-inch Hooker telescope at Mount Wilson, then the largest telescope in the world, and an instrument so massive that its mounting required a dome 12 stories tall and machinery that weighed 500 tons, identified individual stars in the Andromeda Nebula. Among these stars, Hubble recognized Cepheid variables, a class of pulsating stars whose intrinsic brightness could be determined from their period of oscillation, a relationship discovered by Henrietta Leavitt of the Harvard College Observatory through her meticulous analysis of thousands of variable stars in the Magellanic Clouds. By comparing the known intrinsic brightness of these Cepheids with their apparent brightness as seen from Earth, Hubble calculated that Andromeda lay nearly 1 million light-years distant, far beyond even Shapley's expanded boundaries of the Milky Way, and therefore Andromeda was indeed a separate galaxy, an island universe comparable in size to our own. The implications cascaded outward like ripples from a stone dropped into still water. If Andromeda was a separate galaxy, then so were the thousands of other spiral nebulae scattered across the sky, and the universe was not a single galaxy of stars surrounded by empty space, but rather a vast expanse filled with galaxies, each containing billions or hundreds of billions of stars, separated by distances so great that light required millions of years to traverse the gulfs between them. Hubble continued his observations, measuring the distances to more galaxies and also examining their spectra, and in 1929 he published a paper that revealed an even more startling pattern. The more distant a galaxy, the greater its redshift, which according to Doppler's principle meant the faster it was receding from the Milky Way. The universe itself was expanding, with the space between galaxies stretching like the surface of an inflating balloon, a discovery that implied a moment of origin when all the matter and energy in the cosmos had been compressed into an infinitesimally small volume, what critics mockingly called the Big Bang, a term that stuck despite or perhaps because of its irreverent simplicity. The Milky Way, once considered coextensive with the entire universe, now became merely one galaxy among billions, a typical barred spiral galaxy containing somewhere between 200 and 400 billion stars, along with vast clouds of gas and dust, stellar remnants including white dwarfs and neutron stars and black holes, and an unknown quantity of dark matter whose presence could be inferred from gravitational effects, but whose nature remained entirely mysterious. The galaxy's disk, as observations gradually revealed throughout the 20th century, measured roughly 100,000 light-years in diameter and only 1,000 light-years thick at the Sun's location, creating that flattened shape that Herschel had intuited from his star counts. The Sun, along with the Solar System, orbited the galactic centre at a distance of approximately 26,000 light-years, completing one circuit every 230 million years, a period sometimes called a galactic year, which meant that since the Sun's formation some 4.5 billion years ago, it had completed only about 20 orbits, and during the age of dinosaurs our solar system had occupied a different position in the galaxy, a different neighbourhood among the stars. The galactic centre itself, hidden behind obscuring clouds of dust that absorbed visible light but permitted infrared and radio waves to pass through, became an object of intense study once technologies capable of detecting these longer wavelengths became available in the decades after World War II. Radio astronomy, born from the development of radar during the war, revealed that the galactic centre was a source of powerful radio emission, and infrared observations showed dense clusters of stars surrounding the central region. In the 1990s, astronomers using advanced spectrographs on the largest ground-based telescopes began tracking the motions of individual stars near the galactic centre, stars designated with prosaic labels like S2 and S0102, and these observations revealed orbital velocities so high that only an extremely massive yet compact object could generate the necessary gravitational force. The stars near the galactic centre were orbiting a supermassive black hole, an object containing approximately 4 million times the mass of the Sun compressed into a region smaller than the orbit of Mercury, a gravitational singularity from which not even light could escape once it crossed the event horizon, and this black hole, designated Sagittarius A, appeared to reside at the very heart of the galaxy, the point around which everything else rotated. The discovery that most large galaxies harbour supermassive black holes at their centres, objects ranging from millions to billions of solar masses, raise profound questions about the relationship between these gravitational monsters and the galaxies that hosted them. Did the black holes form first, with galaxies coalescing around them, or did galaxies form first, with matter falling toward the centre and accumulating into a massive black hole, or did both grow together in some symbiotic process? Observation suggested that the mass of a galaxy's central black hole correlated with properties of the galaxy's bulge, the spheroidal component of stars surrounding the centre, implying that whatever process formed galaxies also regulated black hole growth, though the precise mechanism remained a subject of active research and spirited debate among astrophysicists whose theoretical models had to account for phenomena occurring across billions of years and involving forces and energies beyond anything achievable in terrestrial laboratories. The structure of the Milky Way revealed itself slowly, layer by layer, like an archaeologist's excavation, with each new observational technique uncovering previously hidden components. The disk where the Sun resides contains most of the galaxy's visible matter, organised into spiral arms, those grand curving structures traced out by bright young stars and glowing nebulae, regions where interstellar gas clouds collapse under their own gravity to form new stars. The spiral arms, despite their apparent solidity when viewed in photographs, are not permanent structures like the arms of a pinwheel, but rather density waves, regions where the random orbits of stars and gas clouds temporarily concentrate, much as traffic jams can form and dissolve on a highway without any individual car remaining stopped for long. As stars and gas clouds enter a spiral arm, their motion slows slightly due to gravitational interactions, increasing the density, and this increased density triggers the collapse of gas clouds into new stars, particularly massive hot blue stars that live only a few million years before exploding as supernovae, but whose intense ultraviolet radiation illuminates the surrounding gas, making the spiral arms visible across intergalactic distances. The Sun currently finds itself between two major arms, in a smaller spur called the Orion Arm, named for the constellation that lies in that direction, though the Sun's orbit carries it in and out of spiral arms over tens of millions of years. A slow cosmic waltz, whose rhythm shapes the history of life on Earth in ways that scientists were only beginning to investigate. Surrounding the disk like a halo, and giving that component of the galaxy its name, lies a roughly spherical distribution of stars, globular clusters, and dark matter extending perhaps 600,000 light-years from the galactic centre, far beyond the visible disk, a vast tenuous realm where stars followed elliptical orbits that carried them high above and below the plane of the disk before falling back through it. The stars of the halo are ancient, formed when the galaxy itself was young, and their chemical composition reflects this antiquity. They contain very little of the heavy elements like iron and carbon and oxygen that were synthesized in the cores of earlier generations of stars and distributed through space when those stars died. The globular clusters, those dense balls of hundreds of thousands to millions of stars bound together by mutual gravity, are among the oldest objects in the galaxy, with ages approaching 13 billion years, formed perhaps only a few hundred million years after the Big Bang itself, and their existence posed a chronological puzzle, because some models of cosmic evolution initially suggested the universe itself might be younger than these ancient stellar cities. The resolution of this age paradox came from improved measurements of the universe's expansion rate, and the realization that the expansion was not slowing down, as gravity should dictate, but rather accelerating, driven by some unknown dark energy that constituted roughly 70% of the total energy content of the cosmos. The precision cosmology of the early 21st century, combining observations of distant supernova, the cosmic microwave background radiation left over from the Big Bang, and the large-scale distribution of galaxies, converged on an age for the universe of 13.8 billion years, comfortably older than even the most ancient globular clusters and consistent with the observed ages of the oldest stars. The Milky Way itself, based on the ages of its oldest stellar populations, formed within the first billion years after the Big Bang, though not in its current configuration, but rather through the merger and accretion of smaller proto-galaxies, fragments of dark matter and ordinary matter that collapsed under gravity and gradually assembled into larger structures. The process of galaxy formation, invisible to direct observation because it occurred billions of years in the past, could nonetheless be reconstructed through a combination of theoretical modelling, computer simulations that track the evolution of millions of particles representing dark matter and gas over cosmic timescales, and observations of distant galaxies whose light, delayed by the finite speed of light, showed them as they appeared billions of years ago when the universe was younger. These observations revealed that galaxies in the early universe were smaller, more irregular, and more actively forming stars than their modern descendants, supporting a hierarchical model in which structure grew from the bottom up, with small galaxies merging to form larger ones over billions of years. The Milky Way's history included multiple such mergers, and the evidence remained written in the sky for those who knew where to look. Streams of stars torn from dwarf galaxies as they fell into the Milky Way's gravitational embrace. Their orbits stretched into long filaments that wrapped around the galaxy like ribbons. Populations of stars in the halo whose orbits and compositions betrayed their origin in separate smaller galaxies that no longer existed as independent entities. And the Magellanic Clouds themselves, those two irregular dwarf galaxies visible from the southern hemisphere as detached portions of the Milky Way, which were actually separate galaxies in the process of being cannibalized by the Milky Way's stronger gravity. The large and small Magellanic Clouds, named for Ferdinand Magellan, whose expedition of circumnavigation brought these celestial features to European attention in 1519, though they had been known to indigenous peoples of the southern hemisphere for millennia, served as laboratories for studying stellar evolution and galactic dynamics precisely because of their proximity, lying only about 160,000 and 200,000 light-years distant respectively. When a massive star in the Large Magellanic Cloud exploded as a supernova on February 23, 1987, designated SN 1987A, it was the closest supernova visible to the naked eye since Kepler's supernova of 1604, and astronomers around the world turned every available instrument toward it, capturing spectra and images across the entire electromagnetic spectrum, from radio waves through visible light to X-rays and gamma rays, documenting the explosion's evolution in unprecedented detail and testing theoretical models of stellar collapse and nucleosynthesis. The supernova's light curve, the change in its brightness over time, matched predictions for the explosion of a blue supergiant star whose core had collapsed to form a neutron star. Though the neutron star itself remained hidden within the expanding debris cloud, its presence inferred rather than directly observed even decades after the explosion. Supernovae, those catastrophic stellar deaths in which a star briefly outshines an entire galaxy, play a crucial role in the chemical enrichment of galaxies because the extreme temperatures and densities in the explosion synthesize heavy elements that cannot form in the cores of normal stars, and the blast wave ejects these elements into space, where they mix with interstellar gas and become incorporated into subsequent generations of stars and planets. Every atom of iron in your blood, every atom of calcium in your bones, was forged in the core of a massive star that died before the sun was born, its matter scattered across space and eventually incorporated into the cloud of gas and dust that collapsed to form the solar system. The Milky Way's interstellar medium, the tenuous gas and dust between the stars, has been enriched over billions of years by countless supernovae and by the gentler element production of smaller stars that shed their outer layers as planetary nebulae when they exhaust their nuclear fuel. The current generation of stars, including the Sun, contains about 2% heavy elements by mass, with the rest being hydrogen and helium left over from the Big Bang. But this seemingly small fraction makes an enormous difference, because heavy elements are essential for planet formation and for the chemistry of life. The interstellar medium itself, far from being an empty vacuum, contains roughly 10 to 15% of the galaxy's ordinary matter, distributed very unevenly with dense molecular clouds, where temperatures drop to a few degrees above absolute zero, and hydrogen exists primarily in molecular rather than atomic form, and more diffuse regions where gas is heated to millions of degrees by supernova shockwaves, emitting X-rays as atoms collide with sufficient energy to strip away electrons. The molecular clouds, dark patches that block the light of background stars and appear as voids or rifts in the Milky Way when viewed from Earth, are the nurseries where new stars form, regions where the density of matter rises high enough that gravity overcomes the outward pressure of gas and triggers collapse. The largest molecular clouds contain enough matter to form tens of thousands of stars and can span hundreds of light years, massive structures that represent a significant fraction of the galaxy's molecular gas content. Within these clouds, turbulence and magnetic fields create smaller condensations, and when a condensation becomes dense enough, it separates from the surrounding cloud and begins contracting under its own gravity, heating as gravitational potential energy converts to thermal energy until the core becomes hot enough to initiate nuclear fusion and a star is born. Star formation, once imagined as an orderly process in which a cloud contracted smoothly into a sphere that ignited fusion, revealed itself through observation to be chaotic and messy, with magnetic fields channeling matter into bipolar outflows that shot jets of gas above and below the forming star's equator, with rotation causing matter to settle into a disk around the protostar, rather than falling directly onto it, and with most stars forming not in isolation, but in clusters containing dozens to thousands of siblings that would gradually drift apart over tens of millions of years, as gravitational interactions sent some members flying off at high velocities, while others remained weakly bound. The Sun likely formed in such a cluster, perhaps in the Orion Nebula or a similar stellar nursery, surrounded by thousands of other newly formed stars whose ultraviolet radiation and supernova explosions may have triggered the final collapse of the cloud fragment that became the solar system, enriched it with radioactive isotopes whose decay products appear in primitive meteorites, and eventually dispersed the cluster so thoroughly that the Sun's siblings now orbit the galaxy on completely different trajectories, indistinguishable from the hundreds of billions of other stars, unless someone were to painstakingly measure their chemical compositions and orbital parameters to search for matches indicating a common origin. The quest to understand the Milky Way's structure and history accelerated dramatically in the late 20th and early 21st centuries as computing power increased exponentially, allowing simulations of unprecedented resolution that could track billions of particles representing stars, dark matter, and gas across cosmic time, and as new instruments both on the ground and in space pushed observational capabilities to new extremes. The European Space Agency's Hipparcos satellite, launched in 1989 and operating until 1993, measured the precise positions and parallaxes of over 100,000 stars, providing the first comprehensive three-dimensional map of the Sun's neighbourhood, and allowing astronomers to trace the structure of nearby spiral arms and to identify stellar streams that indicated past satellite galaxy disruptions. The successor mission, Gaia, launched in 2013 and still operating as of this writing, increased the scale by orders of magnitude, measuring the positions, distances, and proper motions of more than 1 billion stars, roughly 1% of the galaxy's total stellar population, creating a dataset so vast that analysing it required supercomputers and international collaborations involving hundreds of astronomers who published papers describing the galaxy's spiral arm structure, the motions of stellar streams, the orbits of satellites, and even the past close encounters with other galaxies that had sent ripples through the Milky Way's disk like waves on a pond. The Gaia data revealed that the Milky Way had experienced a major collision roughly 10 billion years ago with a dwarf galaxy that astronomers named Gaia Enceladus, or the Gaia Sausage, because its stars filled an elongated region in velocity space on plots that graphed stellar motions. This collision, occurring when the Milky Way was only a few billion years old and still assembling itself from smaller fragments, dumped millions or billions of stars into the halo and may have triggered intense star formation in the disk, fundamentally altering the galaxy's structure and leaving fingerprints in the ages and compositions of stellar populations that persisted to the present day. Other smaller mergers and accretions continue to the present, with the Sagittarius dwarf elliptical galaxy currently in the process of being torn apart by the Milky Way's tides, its stars stretched into streams that wrap around the galaxy multiple times, and with gravitational interactions that may cause oscillations in the disk, contributing to the warped structure observed at the galaxy's outer edges, where the disk no longer lies in a flat plane but bends upward on one side and downward on the other like the brim of a hat that someone has twisted. The warps and asymmetries in the Milky Way structure, once attributed to measurement errors or limitations in the data, emerged as real features that demanded explanation, and the most likely culprit appeared to be gravitational interactions with satellite galaxies, particularly the Large Magellanic Cloud, whose mass, larger than previously estimated, exerted sufficient tidal force to deform the disk. Computer simulations suggested that the Large Magellanic Cloud might be on its first passage through the Milky Way's neighbourhood, rather than being a long-time satellite, having approached from intergalactic space within the last few billion years, and its trajectory and the Milky Way's response to its presence could explain several puzzling features, including the warp, and also the presence of an enormous filament of gas called the Magellanic Stream, that trails behind the clouds like a wake behind a ship, stripped away by the Milky Way's gravity and by the ram pressure of ploughing through the Milky Way's hot gaseous halo. The Milky Way's halo gas, distinct from the stars and globular clusters, also classified as halo components, consists of extremely hot tenuous plasma with temperatures exceeding 1 million degrees Kelvin, heated by past supernova explosions and by the kinetic energy of gas falling into the galaxy's gravitational well. And this hot halo contains a substantial fraction of the galaxy's ordinary matter that had previously been unaccounted for in observations that counted only stars and cold gas. The discovery of the hot halo came primarily from X-ray observations and from ultraviolet spectroscopy that detected absorption lines from highly ionized atoms in the light from distant quasars, those brilliant galactic nuclei powered by supermassive black holes accreting matter, whose light passing through the Milky Way's halo picked up the spectral fingerprints of the intervening gas. This hot halo gas represents the leftovers from the galaxy's formation, gas that fell toward the galaxy but did not cool efficiently enough to settle into the disk and form stars, and it also includes material that was blown out of the disk by supernova explosions and stellar winds, enriched with heavy elements that eventually rains back down onto the disk in a galactic fountain that recycles matter between the disk and halo over hundreds of millions of years. The recycling of gas between different components of the galaxy and the continuous infall of fresh gas from the intergalactic medium maintains the supply of raw material needed for ongoing star formation, without which the Milky Way would have converted all its gas into stars billions of years ago, and would now be a dead or dying galaxy dominated by old red stars with no young blue stars or glowing nebulae. The current star formation rate in the Milky Way amounts to approximately 2 to 3 solar masses per year, a modest rate compared to more active star-forming galaxies, but sufficient to create millions of new stars over 1 billion years. And this star formation concentrates in the disk, particularly in the spiral arms, where gas densities reach the critical threshold for collapse. The rate has varied over the galaxy's history, with periods of more intense star formation triggered by mergers with satellite galaxies that dumped fresh gas into the disk and caused gravitational instabilities that compressed existing gas, and quieter periods when the supply of gas dwindled and star formation declined. But the overall trend has been toward declining star formation, as the available gas is gradually consumed, and as the universe's expansion makes it increasingly difficult for galaxies to accrete fresh material from their surroundings. The future of the Milky Way, projected forward through computer simulations that extrapolate current trajectories and account for gravitational interactions, includes a collision with the Andromeda Galaxy, our nearest large galactic neighbour, currently approaching at a velocity of approximately 110 kilometers per second and expected to arrive in roughly 4 to 5 billion years, an event that will fundamentally transform both galaxies, stripping away their ordered disk structures and merging them into a single elliptical galaxy whose stars will pursue random orbits in a roughly spheroidal distribution, rather than the flattened rotating disks characteristic of spiral galaxies. The collision itself, despite the violence of the word, will pose minimal direct danger to individual stars or planets, because the distances between stars are so vast relative to their sizes that even when two galaxies interpenetrate, stellar collisions remain vanishingly rare. But the gravitational chaos will fling stars into new orbits, with some ejected from the merged system entirely and sent wandering through intergalactic space, while others fall toward the centre, where the two supermassive black holes, having spiraled together through the emission of gravitational waves, will eventually merge into a single black hole containing roughly 10 million solar masses. The merger with Andromeda represents the Milky Way's far future, an apocalypse so distant that it exceeds the human capacity to emotionally grasp such timescales, occurring after the Sun has evolved into a red giant and engulfed the inner planets, after the Sun has shed its outer layers to form a planetary nebula, and left behind a white dwarf slowly cooling toward invisibility. After civilizations, if they survive, will have had billions of years to adapt or migrate or transcend entirely the biological forms that gave them birth. Yet the merger's inevitability, written in the mutual gravitational attraction of two galaxies and confirmed by spectroscopic measurements of Andromeda's velocity, reminds us that the Milky Way is not eternal and unchanging, but rather a dynamic evolving system whose current form represents merely one phase in a life cycle, stretching from its birth in the first billion years after the Big Bang to its eventual transformation into an elliptical galaxy in a universe that by then will be vastly older, larger, and emptier than the cosmos we observe today. The realization that the Milky Way is mortal, that it had a beginning and will have an end, that it has undergone dramatic transformations in the past and will undergo more in the future, emerged only gradually as astronomers assembled evidence from multiple sources. The ages of stars and stellar populations that documented the galaxy's history in stages like tree rings recording seasons. The compositions of stars that revealed the build-up of heavy elements over time as generation after generation of massive stars exploded and enriched the interstellar medium. The kinematics of stars whose orbits preserved the memory of past disturbances and mergers, and the morphologies of other galaxies at various distances and thus various epochs, whose appearances showed the evolution of galactic structure across cosmic time. The field of galactic archaeology, using these fossil records to reconstruct the Milky Way's past, became possible only with the combination of large-scale surveys that provided data on millions of stars, theoretical models sophisticated enough to make detailed predictions, and computational power sufficient to simulate galactic evolution with realistic physics, tools that matured in the late 20th and early 21st centuries and transformed our understanding of the galaxy from a static backdrop for stellar astronomy into a dynamic system with a rich history and an uncertain future shaped by processes operating across billions of years. Among the most profound discoveries emerging from galactic archaeology was the recognition that many stars visible in the night sky did not originate within the Milky Way, but were captured from satellite galaxies that were torn apart by tidal forces, their constituent stars scattered across the Milky Way's halo and disk, where they became indistinguishable by position from native Milky Way stars, but could be identified by their distinctive chemical compositions and their unusual orbits that did not follow the general pattern of galactic rotation. These accreted stars, immigrants from other galaxies, constituted a significant fraction of the halo population and also contributed to the thick disk, a component of the galaxy intermediate in properties between the thin disk where the Sun resides and the spheroidal halo, containing older stars on more inclined and eccentric orbits than typical thin disk stars. And this thick disk appeared to have formed at least partly through the heating of an earlier thin disk by merger events that injected energy into stellar orbits and puffed up the disk's vertical scale height. The thick disk's existence debated for decades because distinguishing it from the thin disk and halo required precise measurements of stellar positions, ages and compositions across large samples, became firmly established through surveys like SDSS, the Sloan Digital Sky Survey, which observed millions of stars and galaxies across a substantial fraction of the sky, and through spectroscopic follow-up studies that measured the detailed chemical compositions of tens of thousands of stars, revealing subtle patterns in the abundance ratios of different elements that traced the enrichment history and origins of different stellar populations. Stars formed in dwarf galaxies showed different abundance patterns than stars formed in the Milky Way itself, because the different timescales and intensities of star formation in smaller galaxies, where supernova explosions could blow out much of the remaining gas and halt star formation, led to different relative contributions from Type II supernovae, which explode quickly after massive stars form and produce large amounts of oxygen, magnesium, and other alpha elements, and Type Ia supernovae, which require longer timescales as white dwarfs in binary systems accrete matter from companions until reaching critical mass and detonating, producing large amounts of iron. The chemical tagging of stars based on these detailed abundance patterns allowed astronomers to identify stars born in the same molecular cloud, even if they were now separated by thousands of light years, to trace the disruption of dwarf galaxies across billions of years by finding scattered groups of stars with matching compositions indicating a common origin, and to reconstruct the Milky Way's assembly history by identifying the contributions from different accretion events and by dating these events through the ages of the accreted stellar populations. This forensic astronomy, teasing apart the galaxy's history from the clues encoded in stellar properties, relied on the fact that stars are remarkably stable over billions of years, preserving in their surface compositions and kinematics the conditions of their birth, even as they orbit the galaxy dozens of times and drift far from their birthplaces, unlike gas which mixes and loses memory of its history on relatively short timescales. The exploration of the Milky Way's structure extended beyond the traditional visible wavelengths, with radio astronomy revealing the distribution of neutral hydrogen gas through observations of the 21 centimeter spectral line emitted when the electron in a hydrogen atom flips its spin relative to the proton, a quantum mechanical transition that occurs spontaneously with a very low probability but becomes detectable because of the enormous quantity of hydrogen in interstellar space. Radio surveys mapping this emission across the entire sky revealed the spiral arm structure more clearly than optical observations could, because dust that obscures visible light is transparent to radio waves, and the Doppler shifts of the hydrogen emission allowed astronomers to measure the velocities of gas clouds and construct rotation curves showing how the orbital velocity of material varies with distance from the galactic center. These rotation curves revealed one of modern astronomy's most profound mysteries. The velocity did not decline with distance as it should if the galaxy's mass were concentrated in the visible stars and gas, but instead remained roughly constant or even increased slightly in the outer regions, implying the presence of substantial additional mass that did not emit light. The dark matter whose existence had been proposed decades earlier, but whose nature remained completely unknown. Dark matter, constituting roughly 85% of the total matter in the universe, pervades the Milky Way in a roughly spherical halo that extends far beyond the visible disk, perhaps to distances of 600,000 light-years or more, its presence detectable only through gravitational effects. The rotation curve that remains flat instead of declining, the velocities of satellite galaxies orbiting the Milky Way, which require more mass than the visible matter can provide, and the motions of stars perpendicular to the galactic plane, which indicate the vertical gravitational force, and thus the local density of matter. Despite decades of increasingly sensitive experiments searching for dark matter particles, using detectors deep underground to shield from cosmic rays, looking for signals from dark matter annihilation in the galactic center or in dwarf satellite galaxies, and attempting to produce dark matter particles in accelerators like the Large Hadron Collider, no direct detection had been confirmed as of the early 21st century, leaving the composition of dark matter as one of physics' greatest unsolved problems, a gap in our understanding of the fundamental constituents of nature, the failure to detect dark matter particles, despite theoretical predictions that they should interact weakly with ordinary matter and occasionally scatter off atomic nuclei or produce faint signals from mutual annihilation, led to increasingly exotic proposals. Perhaps dark matter consisted not of a single particle species, but of multiple types. Or perhaps it was not particulate at all, but rather some manifestation of modified gravity on galactic scales. Or perhaps the dark matter particles interacted even more weakly than the most optimistic theories predicted, and would require detector masses or observation times beyond current technological capabilities. But the gravitational evidence for dark matter's existence remained overwhelming, observed not only in the Milky Way but in every galaxy and cluster of galaxies where measurements were possible, and in the large-scale structure of the universe itself where dark matter's gravity shaped the cosmic web of galaxies and voids. The cosmic web, that filamentary structure of galaxies aligned along intersecting sheets and filaments surrounding vast voids, emerged naturally from the growth of structure under gravity starting from tiny density fluctuations in the early universe, fluctuations whose imprint remains visible in the cosmic microwave background as temperature variations of a few parts per 100,000, and computer simulations showed that dark matter, because it does not interact with radiation, and therefore began collapsing earlier than ordinary matter, which remained coupled to photons until the universe cooled enough for atoms to form, provided the gravitational scaffolding upon which galaxies formed. The Milky Way sits within a filament of this cosmic web, part of the Laniakea supercluster, a gravitationally bound structure containing hundreds of thousands of galaxies and spanning roughly 500 million light-years, though the accelerating expansion of the universe driven by dark energy means that structures on such scales are not becoming more tightly bound, but are instead approaching a state of maximum extent, and galaxies in distant parts of the cosmic web are receding from us ever faster as space itself expands, carrying them toward a horizon beyond which they will become forever unreachable, as their recession velocity exceeds the speed of light, not through motion through space, but through the expansion of space itself. The Milky Way's position within the cosmic web and within the local group of galaxies, which includes Andromeda and several dozen smaller companions, determines its ultimate fate not only through the impending collision with Andromeda, but also through the larger-scale dynamics of cosmic expansion and the eventual heat death of the universe. As star formation consumes the available gas, existing stars exhaust their fuel and die, and the temperature of the cosmic background radiation continues to decline as the universe expands, asymptotically approaching absolute zero over timescales that dwarf the current age of the cosmos by factors of trillions or more. In such a far future, perhaps 100 trillion years hence, the merged remnant of the Milky Way and Andromeda will be an island of fading stars in a vast darkness, with all other galaxies outside the local group having receded beyond the cosmic horizon, their light stretched to such long wavelengths by expansion that no conceivable detector could register it, and any civilizations existing then would see a universe containing only their own galaxy, surrounded by empty space, with no evidence of the billions of other galaxies that populate our current observable universe. And they might reasonably but incorrectly conclude that their galaxy was the entire universe, just as humans once believed the Milky Way constituted the entire cosmos. The irony that future observers, despite possessing potentially far more advanced technology than our own, would have access to less information about the universe's history and structure because crucial evidence would have literally disappeared over the horizon, reminds us that we live in a privileged epoch for cosmology, able to observe the cosmic microwave background, to study galaxies across a wide range of distances and thus cosmic epochs, and to piece together the history of the universe from the Big Bang through the formation of galaxies and stars to the current era. This privilege carries responsibility. The knowledge we gain through current observations represents information that is time-sensitive, that will become unavailable to future generations unless we preserve not just the data, but the context and understanding necessary to interpret it, a legacy to descendants who might otherwise be unable to reconstruct how the universe began, or how it evolved, or even to determine that the universe is expanding and had a finite beginning. The study of the Milky Way thus serves multiple purposes. It satisfies the human impulse to understand our cosmic environment and our origins, tracing the chemical and physical processes that transform the simple mix of hydrogen and helium, emerging from the Big Bang into the complex structures capable of supporting life and intelligence. It provides the nearest and most detailed example of galaxy formation and evolution, a laboratory where physical processes can be studied in greater detail than in more distant galaxies, and it connects us to the larger universe, showing our place within the cosmic web and within the timeline of cosmic history, neither at the centre nor at any privileged location, but rather typical citizens of a typical galaxy, in a vast cosmos containing billions of galaxies, each potentially hosting billions of planets, a perspective that is simultaneously humbling in its demonstration of our cosmic insignificance and elevating in its revelation that we are capable of understanding our situation, despite the vast scales of space and time involved. The wonders of the Milky Way, revealed through centuries of increasingly sophisticated observation and theory, encompass phenomena across an enormous range of scales and energies, from individual stars in their variety, including the massive short-lived blue supergiants that live only a few million years but shine with the luminosity of hundreds of thousands of suns, to the dim red dwarfs that burn so slowly they will outlast the current age of the universe many times over, from the violent deaths of massive stars in core-collapse supernovae that briefly outshine their host galaxies, to the quiet fading of sun-like stars into white dwarfs that cool gradually over trillions of years, from the dense stellar environments of globular clusters where stars are packed so tightly that planetary systems might be disrupted by near passes of neighbouring stars every few million years, to the lonely spaces between spiral arms where stars wander in relative isolation for hundreds of millions of years between crossings, from the titanic supermassive black hole at the galactic centre, whose gravity dominates the orbits of millions of stars in the central bulge, to the stellar mass black holes scattered throughout the galaxy as remnants of dead massive stars, from the diffuse hot halo gas containing as much mass as all the stars in the disk, to the dense molecular clouds where star formation proceeds, and where complex organic molecules form in the chemistry of interstellar space. Each of these phenomena, worthy of lifelong study, connects to others in a web of physical relationships that spans the galaxy. Supernova explosions enrich the interstellar medium with heavy elements, but also compress gas clouds and trigger new star formation. The newly formed stars emit ultraviolet radiation that heats and ionizes surrounding gas, creating glowing nebulae, but also disperses the residual gas, preventing further star formation in that region. The most massive stars die quickly and leave behind neutron stars or black holes, whose accretion of matter produces X-rays that can be detected across the galaxy, while the less massive stars live for billions of years and provide stable sources of energy that could sustain planetary systems capable of developing life and intelligence that might eventually look outward and wonder about their place in the universe as we do, the narrative of the Milky Way is not a simple story with a clear beginning, middle and end, but rather a complex braided history of processes operating simultaneously on different timescales. The 10 billion year aging of individual stars, the 100 million year evolution of spiral structure as density waves rotate through the disk at a different rate than the stars themselves, the billion-year timescale of satellite galaxy accretion and merger, and the 10 billion-year history of the galaxy's evolution from a chaotic assembly of proto-galactic fragments to the mature spiral galaxy we observe today, a galaxy that will continue evolving over future billions of years until its merger with Andromeda and its eventual fate in a universe growing ever colder and darker as stars exhaust their fuel and expansion carries the scattered galaxies ever farther apart. This ongoing evolution, far from being merely an abstract concern for theoretical astrophysicists, has direct implications for life in the galaxy, including life on Earth, because the local environment changes as the solar system orbits the galactic centre, passing through spiral arms every few 100 million years exposes the solar system to increased rates of nearby supernovae, which might affect Earth's atmosphere and climate. Passing through regions of higher stellar density increases the probability of encounters that could perturb the Oort cloud and send comets plunging toward the inner solar system, and the gradual evolution of the Sun itself as it slowly brightens over billions of years will eventually render Earth uninhabitable even without any external galactic influences, though on timescales that remain measured in hundreds of millions to billions of years. The detailed mechanisms by which galactic environment might influence the development of life on Earth remain subjects of active research and spirited debate, with some researchers proposing that mass extinctions correlate with passages through spiral arms, or with the solar system's oscillations above and below the galactic plane, while others argue that the effects are too weak or too rare to significantly impact the overall course of biological evolution. But the possibility that galactic astronomy and paleontology might intersect, that the fossil record of life on Earth might preserve signals of cosmic events that occurred millions of years ago, represents one of the more intriguing frontiers where multiple scientific disciplines converge to address questions that no single field could answer in isolation. The wonder of the Milky Way lies not only in its scale, its beauty, or the exotic phenomena it contains, but also in the intellectual journey that has carried humanity from the earliest observations of that luminous band across the night sky to our current understanding of a vast rotating disk of stars, gas and dark matter, a journey that required the development of mathematics, physics, chemistry and technology, the patient accumulation of observations across generations, the willingness to discard cherished ideas when they conflicted with evidence, and the imagination to conceive of scales and processes far beyond everyday human experience. The journey from mythology to cosmology that represents one of the great achievements of human civilization, and continues into an open future where new instruments and new theoretical insights promise to reveal phenomena we have not yet imagined, and to answer questions we do not yet know how to ask properly.